All right, in our first video, we've described how the mass on a spring moves, but the big question that arises is what causes it to move this way? But it's really important that maybe you write this down. You're like, hey, the acceleration of a mass on a spring in a horizontal fashion. We are talking about the system where you pull the spring back and then you released it and it just oscillates back and forth like that. So this is the acceleration equation that describes that situation. But the big question is, well, why does it move that way? And so we said this is how it moves. That's the kind of the description of its movement, but what's the why? Well, let's look at some forces to describe this. So we know the force of a spring is equal to negative kx. And let's just relabel some of these things. This is going to back in your brain. So x is how far you stretch it or compress it from equilibrium, all right? Because it wants to hang out if it's just an equilibrium, x equals 0, there's no force from the string. It's happy, all right? As soon as you stretch it, then it wants to fight you in the opposite direction. So if I pull it to the right, the spring tries to pull back left, and that would be the negative right there. So that negative doesn't mean that it's always going left. That negative just means whatever you do to it, if I compressed it, it'd want to put a force to the right, which would be a positive force. So the common misconception is people think, oh, I just call force spring negative all the time. No, that negative is there is because it's a restoring force. It wants to get back to its equilibrium, all right? And then this K, that's your spring constant measured in newtons per meter. And just think about this. If you have a high K value, that means it's a very rigid spring. If you have a low K value, that means it's more like a loosey-goosey kind of thing. And just some things to remember back in the day, if you ever have a force function, you integrate it, that gets works equal and opposite to change of potential energy. So the potential energy function of a spring is 1/2 kx squared. All right, so we're gonna say, why does the mass in the spring move the way it does? Let's look at our FBD. Whenever you're in trouble and it's a force situation, you draw an FBD. That's a really good thing to help out. So you have a mass on a table and there's a spring. You have force gravity acting from the center of mass downward. And as soon as that block touches the table, you have the normal force pushing upward. And technically the normal force is occurring between the block and the table right there. So if they ever say draw it where it occurs, it's down here. I just always move it up here just so I can see my diagram better. And then that's a result of Newton's third law. And then I put F spring right there. And I'm kind of picturing it just as I release the block. So immediately as I release the block, it has some force spring. And the reason I'm saying that is because it gets back toward equilibrium, that force eventually shrinks to 0, which means acceleration at equilibrium would be 0. But here's the deal. We draw a picture, we label our forces, we show our coordinate system, our 5 steps for success, and then we sum our forces. And there's not much going on in the y direction, so I'm not really going to look at that right now. But let's look at the x direction. I have negative kx equals max. So some things to notice right here. I had horrible whiting out. Your acceleration, this acceleration is proportional to displacement. So if I displace this, if x is huge on this side, that means a is going to get big as well. So if I pull this spring really far away from where it wants to be, as soon as you release it, it's going to have a huge acceleration to get back toward equilibrium. So acceleration is proportional to x. And really I put in parentheses, so is force. The force is proportional to x because remember, the reason it has a net acceleration is because it has a net force. So if you want to write down this really important postulate, this really important number 1 here, acceleration is proportional to displacement, but really force is also proportional to displacement. All right, but a secondary note here, and the direction of the acceleration is opposite of the displacement. So you're like, oh, if I pull it to the right, so it's displaced to the right, that thing wants to accelerate back to the left. So it's really important you put this down. The direction of acceleration is opposite of displacement. If I compress it to the left, it wants to accelerate to the right because that'd be a negative value for x. If you compressed it, negative times a negative, make it a positive acceleration. So these 2 important tenets right here, when 1 and 2 are true, simple harmonic motion results. And that's fancy talk for it's just going to oscillate back and forth. But these 2 tenets have to be true. It has to be proportional to displacement, not even displacement squared. If this was an x squared right here, and this was an a, simple harmonic motion would not result. If this was a cubed or something weird, this is 2 very special conditions. A has to be proportional to x, and a's acceleration direction has to be in the opposite of the displacement. Okay, so that's this is a very important topic in physics. So write that down. Make sure that you write down this vocab, simple harmonic motion results. It's going to oscillate back and forth. And technically, I just took this right here and I rewrote it. I said, you're negative kx, and we write x, but really, the x, it's a function that depends on time. So I kind of oversimplified it there by saying, oh, it's just x and that's just a. This is a position function that depends on time, equals m times a, which depends on time. So I said that right there, and I just rearranged it, and I said, hey, in this, once we say why is it moving this way, we say we summed our forces. Well, acceleration equals negative k over m times your position function. So you're like, okay, so using forces, we got another expression for acceleration. And that's important. So in our first video, we got an expression for acceleration involving the sines and cosine kind of stuff. And then in this video, use summing forces, we got another expression to describe the acceleration. So I say, well, from before we know that A of t also equals that. That's also a true statement. That's good physics we use to get there. It's good physics we use to get there. So if you look at this expression, you look at this expression here, they both have an A. They both have an A. They both have an x of t. They both have an x of t. And you might be like, well, to make this, they both have a negative. They both have a negative, okay? So to make this true, you must realize, well, your angular frequency, your omega squared equals k over m. So that's where I want us to go, is to know that if we ever have angular frequency and we know the mass, we can solve for the spring constant. Or if we ever know the angular frequency and the spring constant, we can solve for the mass of the object oscillating back and forth. So I will say, this is the mass of the object oscillating back and forth. We kind of treat our springs as kind of massless, but truth be told, it gets more complicated if you account for the mass of the spring. So let's not go there today. But here's something kind of cool. We know this relationship, so if we square root both sides, we know omega is the square root of k over m. So very important to write those down. And all I'm doing is just kind of deriving some equations that are going to come in handy later. One little thing, they might write it, like this looks really complicated, but A of t, if they said, oh, equals negative 16x of t, you're like, whatever number is out front, and yeah, there's a negative there. That just means it's whatever way the position goes, the acceleration's in the opposite direction. That number right there, that could be your k over m number, or it could be your omega squared number. So you're like, just to kind of show this, if 16 equals omega squared, because it's the number in front of the position function, that means omega's 4, all right? And a lot of people are like, oh, there's a negative. No. The negative is part of the whole form of the deal there. Whatever number is in front of your position function, that is your omega squared, or it's your k over m. All right, so that's a lot of information, and we have to practice with it. I just want to point out some things. So if you would just watch the first video and you watch the second video, you're like, that's a lot, go back and look over your notes before I kind of finish it up here, because this is a lot of information to take in all at once. All right, so just to finish here, we went through in our first video of the series here, we said there's our position function, there's our velocity function, there's our acceleration function. And we gotta ask ourselves, in physics, we always like to talk about when we throw a ball, what's the maximum height it reaches, or the minimum height, or whatever. We always like to talk about maximums and minimums. So what I wanna talk about real quick is your maximum position, your maximum velocity, your maximum acceleration, and then the minimums of those things as well, just to kind of highlight some different extremes, okay? So if you're looking at your position function right here, we said the greatest this could ever be is when cosine is 1, this function is 1. So that means we said, oh, x max is a, x min is negative a. Well, let's look at our velocity function. And I just realized I wrote in the margins here, so maybe you already wrote this down, but I never talked about it, but let's talk about it now, is that your velocity function, once again, the biggest sine can ever be is 1. So if you're like, okay, that's 1, and then 1 times that, well, there's a negative there now, so that's actually going to be the minimum. So the minimum for velocity is negative a omega. And if sine were a negative 1, the biggest your velocity function can ever be is a times omega. So we're just looking at the number, this out front, we're saying this function is 1. And then you look at acceleration, you play the same game. The biggest or the smallest a cosine function ever be is 1 or negative 1. So let's say cosine was negative 1 here, negative times a negative. So your max would be a omega squared, your min would be negative a omega squared. So I kind of put that together in a little summary right here just so you can look at it side by side. So sometimes in the AP test, they might say, hey, for this system, what's the greatest it could ever be displaced? Well, just look at the amplitude. How far do they pull it from equilibrium? It's never going to go farther than that. Okay, it's just like you can never climb a roller coaster hill that's taller than your first hill, unless there's some other force acting on the system to add energy in. And there's your V max and your V min, your A max and your A min. So those are just good things to have on hand. All right, so we derived that using the sine cosine method. And then one little thing we learned from the force method that we added just a little bit earlier is we said, well, acceleration also equals negative k over m x of t. So we're like, oh, okay, and x of t was that cosine omega t plus phi situation with the a right there. So one other thing we know about acceleration is that we can also have, if this were 1, the biggest acceleration or smallest it could ever be is ka over mass. So one other thing I'd like you to add on is, and this is a lot, is that the biggest the acceleration could ever be is your spring constant times your amplitude divided by the mass. Or the smallest could ever be is your spring constant times the amplitude divided by your mass with a negative out front. So if this green stuff makes sense, awesome. I think that's all the further they're going to take it on the AP test. I have never really seen them dig into this part of it, but it's helpful. We're just kind of getting the last percentage points of the content in the AP Physics C test. If this doesn't really make sense, I think it does, because your math brains will kick in. You're like, oh, if this is A and the biggest this cosine function of B is 1, that means the stuff out front is the max or the min. So if you like that, great. If you're not, don't lose sleep over it. The last thing I want to finish with here is that when we have this shape of the graph, that's what we've done in math class for many years now. You can kind of reconcile your calculus knowledge with your physics knowledge. So I want to talk about our physics situation first. And there's a lot going on in this picture, but I'm going to explain as we go. So, and I did not draw the spring because it was cluttering up my picture, but there's a spring attached to this. And let's say the mass of the spring is handled equilibrium, and you apply a force and you stretch it out to this position right here. All right? So at this position, our physics brains say it has maximum potential energy because it's pulled back, and I'm about to release it. But if you have max PE, just like a roller coaster car, you're at the top of the hill. You have minimum kinetic energy. And as you release it, and as it goes, it starts to speed up. So its potential energy goes down, its kinetic energy goes up. And at this point right here at equilibrium, technically there's no force acting on it right there because the x value is 0, so it's not going to accelerate anymore. It's reached maximum velocity, which means it has 0 acceleration. And when you know it's reached maximum velocity, now it has maximum kinetic energy and minimum potential energy. All right, so I made a little note there. The A is 0 there because the x at that point now is 0, which if you have no net force, you have no net acceleration. So your velocity is going to be what it's going to be, and we know it's maximum velocity right there. And then all of a sudden the spring starts compressing, right? So it starts slowing down, and at the very end when it's reached maximum compression, you have max PE and you have minimum kinetic energy. So it's just kind of like a roller coaster car going up and down the track, except now we have something oscillating back and forth, a mass and a spring. And once again, I did not draw the spring. So that's the physics picture going on. So much good physics. And you could say the A is negative Ka over m, and it's negative because it's going left. You pull it to the right, but then it wants to accelerate back to the left. Here, the acceleration is maximum. You're compressed, and it wants to push you back to the right because that's that restoring force. It wants to get back to equilibrium. And then your calculus brains are like, well, the graph would look like this. It starts at A, it goes, and this is a horrible graph. This is just freehanded. It goes down to 0, then to negative A, and back up to A. And this is assuming no friction. If there were friction, it'd be kind of a damped oscillator, and it'd shrink down to 0. You can picture that. That'd be kind of a cool picture to draw, but don't have time to do it today. But here's the deal. Our graph was this. It was a cosine graph. Think about the tangent line to find velocity. So here, the tangent line is 0, and that makes sense. It starts off at 0, and then you release it. And as you release it, it keeps going faster and faster and faster. And it reaches top speed right about there. Oh, I'm off the screen. Top speed right about there, and I should use the smaller pen. And then all of a sudden it starts slowing down, point of inflection, I think they call it in calculus. I forget. And then right there, it's got a velocity of 0 because that's what our graph says right there. And then it changes direction, and the slope goes like that, and it starts coming back this way, this way, this way, this way. And eventually, then it reaches a certain point. It's not really speeding up the same rate, and then it goes, and it gets back toward a slope of 0 right there because it pauses once again there. And so it's kind of cool because your calculus brains line up with your physics brains, and that is what's cool about AP Physics and AP Calculus because they all work together. The mathematical model describes our physical situation, and that's really cool. All right? And this is not a real life situation because in real life you'd have friction on the table, and it's what they call a damped oscillator, so it'd start here and it'd never get back. And once again, I did not draw the spring in this situation because, yeah, I didn't want to clutter up my picture. And just picture this. Why does it have potential energy? It has max potential energy because some outside force did work on your system to put it at that point right there. And so once you put the work in, now it has PE, you release it. PE transforms back and forth, PE to KE, but the overall sum, if you add this, it'd be some number. It'd be the same number in that because energy cannot be created or destroyed from our system. So thanks for watching.